Okay, for the class activity today, I wanted to build a little, it's going to be kind of like a little operating system basically, and it gets commands from the UART, and then it just does some function based on them. So it'll receive a character or maybe a couple characters, and then it'll perform a function based on them. It's kind of like if you ever use DOS or a Linux terminal and you type in a command and it might have some arguments and you hit enter and it does a function. Behind there's the terminal server program that just reads whatever you're typing and then looks through the file directory for a executable with that name. So we're going to do something kind of similar, but I just want you to think about which C directives you might use to implement this sort of thing. And you can pretend like you have functions already that get characters and can send characters from the UART. And so just thought it would be interesting to think about a command interpreter, basically. So the command interpreter will be C interp, and it'll take a character, CMD we'll call it, and then one way to do it would be to have a select CMD. This is a C directive, and then have a bunch of cases, and I'll let you fill in the rest. Another way to do it would be if CMD equals some character, let's say S, then we do the S func, else if CMD equals C, then we do C func dot dot dot, and you can implement however many you want. So you might want to look at the select statement in C, or if-then statements, and think about receiving some characters over the UART to do different things. Oh, is it switch? Is it actually called switch?
Yeah, I think it's switch.
Oh, sorry everyone.
I think it's switch. Yeah, switch statement.
Yeah, the UART receive function is hard. Oh, yeah, I suppose. That's right. Yes, maybe you could write down the steps for configuring the receive function. Does the command, which do you think is the hardest part?
Well, I don't remember that. I remember how to do the UARTs receive function from yesterday.
That's right. We'll go over that again.
I mean, I still don't get UART.
Yeah, that's fine. Do you remember any of the steps for configuring the UART?
No.
So what might you need to do, since it's a physical pin, do you remember what you need to do to configure a pin as an input or an output?
And I know I need the trace function.
Yeah, the tris register, you need to write to that. And to receive something,
I would have to type it as 0, 1. I have to put a 1.
a 1 means input, right?
Yep. Or at least that's what the TA told me. When I asked him about that on Monday.
So 1 means input. Do you remember, did you look at the peripheral pin select at all? Connecting the peripheral to a certain pin? Yeah, it's kind of complicated. But basically you need to set up the peripheral pin select register too. It's just like the tri-state register, except it just connects a certain peripheral to a certain pin. So that would be step 2, maybe. Step 3 would be to enable any interrupts. And then step 4 maybe would be to configure the baud rate generator. You know, how fast the UART is going to send and receive data. And then the final step would be to enable the UART module, so then it's starting. And you're pretty much done. So it's maybe 5 steps. If you're not using interrupts, then you don't need to configure interrupts. So it might be 4 steps. Thoughts over here? Yeah, that's okay. Do you remember the switch statement from C? Okay.
Do you understand?
Yeah, so the switch would be a function would like get a character, and then it would send it to a command that would switch based on the character that you got from the UART. So the idea is you could have your computer connected to the PIC, and then you could send a new command or do the configure.
Well, sure we're gonna need. Okay,
Any thoughts over here?
Some thoughts, a little bit of worries.
Yep. So yeah, that's the hard part I think at this point is setting up the UART. I mean, after you do it a few times though, that doesn't seem very hard. It's just copy and paste.
That's the actual digital thing.
Yeah. So we gotta initialize. Well, it's receive and what do we need?
thoughts over
Yeah,
here?
you should do both. Do both.
Read data into mem register, switch.
It's actually not the
Yeah.
I want to set the bit output at the beginning though, maybe? Or, yeah, let's see. To send to transmit data. Yeah, they're different pins usually. I don't think it would work with the same pin. It might though. I'm sure it's been done. Yeah, but normally it's two different. I don't want to transmit and receive. So you do the tri-state thing. You configure the UART. How many things do you have to write to configure the UART? Do you remember? There's the UART mode register. Yeah, UART mode. Yeah, but I mean.
So U1 BRG, what battery do we want?
UART mode, and then there's
You want,
UART states, I believe. Then there's the UART BRG register, which is the baud rate generator register. Yep. Then there's the peripheral pin select registers. So yeah, it actually is a lot of stuff. Then if you're doing interrupts, you have to set the interrupt flag and interrupt enable registers.
Oh, frequency. Yeah. So it's 16 measures. So we have to set that UXBRG plus 1 UXBRG.
Did you see our issue?
What are we going to use it as a U1?
No.
It's like R8.
Oh yeah.
R8 stock.
Yes. RA9 doesn't work. RB9.
So we're going to use U1 BRG equal.
In 10, 11.
What do we put? 9600?
Have you been
Equals the
doing
battery.
anything like with the pull-up resistors? Have you read about that in the data sheet? It could be an issue with
Think
pull-up
right now.
resistors not being set up,
I'm 16.
but or it could be just the pins are bad.
We got that. So 103.
Oh, okay. It could be the pull-up resistors. It could be the peripheral pin select register isn't written correctly. It could also be that the AD con register has them configured. Maybe after class, if you have time, we can do some debugging. Has the lab TA offered any help?
We talked to him. He ran through some things, and I don't know, like we fixed the breadboard. I got him to talk about the flow through the series at one point. I can't remember what he said though.
Oh, okay.
He said a lot of stuff.
Okay.
He does.
Yeah, I mean, but is the rest of the lab working okay otherwise?
Yeah, it seems that way.
Oh, excellent. Yeah, I mean, let me know if you have problems. But if the rest of the lab is working fine,
Yeah.
equal 103, we'll figure out what's going on.
So what does he kind of say? Our final result for this project was 2 LED shorts.
Right. So just take those results and then get rid of 2 of the top bits. And
Why
then
you taking interest
or you can put them on different pins. Yeah, that's all. I mean, if you're willing to put in some extra work, that's fine. Yeah. Otherwise, I should have some time today. Maybe I'll stop by the lab section today. Are you in today's section? At 12. Okay. Maybe I'll stop by and see if I can.
You're right.
some
Okay.
stuff.
Yeah, I mean, it sounds
Okay.
Why did we not think, where did I use it?
All right, so I think we'll kind of get started with the class. So for the UART receive function, did anyone count the number of steps that you have to do to configure the UART to receive? how many registers do you have to write, basically, without interrupts? So we'll do UART config. What's step one? Anybody want to take a crack at what step one would be, maybe?
Write appropriate values for data parity and stop bits, or
Data parity and stop it. So that would be in the UART mode register. I guess you could do that first. I was kind of thinking first, what about the input and output pins? The tri-state register, right? Or maybe I'll write the AD con, right? And tri-state registers that you want to pick for inputs and outputs. And so 2, we haven't talked about this much yet, but 2 would probably be peripheral pin select. So basically you want to pick what pins you want to use for RX and TX. So these 2 steps here are kind of related. You have to check the peripheral pin select, and there's a nice table in the data sheet that shows you which pins you can use for peripherals. And then you write to the peripheral pin select register and basically connect those to the PIC. Alright, so we have this UART module inside. We've got an RX and a TX pin, and then it's inside the PIC. Say we want to use pins 15 and 16. So then we write to the PPS register, and that will connect these pins to these pins. So the first thing we want to do is configure these correctly. So if this is RX and this is TX, and these are also RB, I don't remember, RB9, RB10, let's say. Is that right? Okay. So let's say these are in port B, then we would write tris B for these pins, and TX would be we would write that as a 0 because that's an output, and RX would be 1 because that's an input. So the first step is we configure those pins to be digital. Then we set the tri-state register to set them as the right pin direction. Then we connect them to the peripheral with the PPS register. And then we can start writing the UART. So the first thing we probably want to do is write the U1 mode register. And that will set up the baud speed, the parity, or basically just the parameters for RS-232. So we set U1 mode to be for RS-232, basically. And then we, let's see, then we want to do U1 BRG. And that sets up the baud rate. And then U1, I think it's called U1 state. And that sets up the rest of the RS-232 parameters. And then 6 would be enable, which is in the U1 mode register. Let me just double check. Let's see, so set the number of data bits, that's in U1 mode. Okay, so it's called U1 STA. And so you don't want to enable transmission until you've set up all this other stuff. So you enable U1 mode and U1 state. So that's your final step. So it's like anything else, you do it the first time and it seems complicated, but after you write it once, then you don't really have to look at it again. You could even write a function that, an initialization function where you could just pass it a baud rate that you want, and then it would calculate, the function could calculate VRG for you. If you're clever, you could maybe even write it in defines in C directives, and so it would calculate the baud rate before it programs the chip, and then just plug in the correct number. And I think that there used to be a C header file that Microchip provided that would do all this stuff for you. But it's probably out there somewhere. But in this class, we're trying to do everything ourselves. So. Okay, so any questions about the activity? And then for interrupts, it's another bunch of steps. You have to make sure that the global kind of interrupts are enabled and the correct priority is set. And then you enable the specific interrupts related to sending and receiving. In the discussion section, we just did one function as an interrupt, and the other one we just implemented manually without interrupts. Anything else we would need to do? I think that's it. Okay, so I want to talk a little bit about RS-232. I think for everyone in the class, this is like ancient technology. It was for me at the time, but it still gets used in engineering in an engineering environment just because it's been around so long. These days, there's chips that do RS-232 over USB, so you don't really have to know much about either one. But basically, it was developed as a common interface in the 1960s, and it was designed for connecting like a terminal server to a mainframe server. Let's see. In the old days, that's how it used to be because nobody could own their own computer. You just could use like a terminal somewhere, and it connects to the more powerful computer in the build that takes up like an entire room in the building. So this was actually designed to connect your little terminal to the mainframe, RS-232, and people just got so used to using it that it's kind of crazy. Like something that was designed for a mainframe to a terminal now gets implemented when people are designing like microprocessors. They're like, okay, we need to implement this ancient technology in tiny transistor circuits in our microprocessor unit. I think it's kind of crazy. These days, there's chips that implement USB inside the chip as well in hardware. But RS-232 is kind of like the building block. And the terminology for RS-232 is one of the ends of the interface is called the data terminal equipment, or DTE. The other end of the interface is called the data circuit terminating equipment, or DCE. They could call it data terminating equipment, but I mean, that's confusing. I don't really know why they call it data circuit terminating equipment either, because it's also confusing. Basically, DCE is the mainframe side, and DTE is the terminal side. For the purposes of our class, which do you think is the mainframe? Your computer or the PIC? Why do you say that? I mean, it doesn't really matter. It's just making sure that the RX and TX are pointed in the consistent direction, basically. So for our class, the PIC is actually the mainframe computer. So our PIC is our supercomputer, and the computer that we connect it to is the terminal. And that's basically because we're reading and writing to the PIC when we open up a little terminal program in our computer. So when we open up a little terminal program, that's like a little terminal client for the PIC, reading and writing to the PIC. That's kind of the idea. Even though the PC that you connect the PIC to is quite a bit more powerful than the PIC. That's just some terminology. So the RS-232 connector, in the lab, I believe you'll have a USB to RS-232 converter, which you can put on your breadboard. Does anyone have them already, or do they get provided in the lab? I should probably know that. Nobody has them. Okay. So you may or may not have to wire this up, but basically pins 2 and 3, if you look on the connector, are the RX and TX. The rest of the pins don't necessarily need to be implemented. That's one of the things about RS-232 is it's been around so long that there's no real common implementation, and so as long as the client and server are in agreement about the implementation, then it's okay. But in general, it's not a very strict implementation. USB, on the other hand, is extremely strict, and so that has to be the same across a wide variety of devices. So, I mean, USB is kind of more universally used, and so it makes sense that it would be a stricter implementation. But RS-232 is kind of like an engineering, specification. So you can use it in the lab, you can change it around, you can use it with a wide variety of equipment. So it's pretty useful. Let's see. So the DB9 pinout, that's that little 9-pin connector that you might see on the back of some older computers. It says serial or I/O on it. These are what the pins mean. There's a line signal detect that basically tells if it's connected to anything. There's transmit, there's receive, there's DTE ready. So you send a signal up when you're ready to receive data. And there's a signal ground, which makes sure that both computers are at the same voltage level. There's DCE ready, that's the other side saying it's ready. And there's clear to send, which is similar to DCE ready, but it's that's more for when you're processing individual bytes of data, and request to send. So there's actually quite a few different protocols for data flow control using these pins, sending bytes to each other. We're not going to really use any of them. We're not going to do too much with flow control or clear to send, DTE ready. We're just going to send and receive data in the simplest way possible, just so we can get like a hello world up and running. Okay. So this is not a communications class. We're just going over a particular microcontroller in detail. There's also a ring indicator. I don't really know what that does, but I think in principle it was designed to be like a phone call, so you can send a ring to a terminal. And these are kind of, this is a connection diagram. So you can see it's just the top two that we'll really be using. The other pins we won't be using too much. So this is what a frame for RS-232 looks like. There's 1 bit that's a start bit. There's 5 to 9 bits for data. There's potentially 1 bit for parity, and then there's 1 to 2 bits for stop. For us, the hardware takes care of all of this. Okay, we just put a byte in the transmit register, and it sends it. We don't have to worry about it. But this is what it's doing basically. It's sending a start bit. It's sending 8 bits of data. Sending a stop bit. Then another start bit, and another 8 bits, and then stop. That's what it's doing each way. Any questions so far about RS-232? Okay. So the hardware is going to take care of most of it. So some common baud rates for RS-232. 9600 is the most common baud rate that you'll see. If you've got like a terminal program on your computer, often the default is 9600. What sorts of terminal programs are people using these days? Does anyone know what's on the lab computers? Has anyone used a terminal program to do serial before? Yeah. Oh. PuTTY, yeah, that's the one I've always used. It's free. I think 9600 is standard for PuTTY RS-232. Windows used to have something called Hyperterminal. I don't know if anybody used that. It was kind of like a worse version of PuTTY, basically. Yeah, that's like in the 90s, everything was hyper. That meant it was high tech. So for Linux computers, you can connect the Linux terminal directly into one of the terminal server ports, and it'll work just like PuTTY or Hyperterminal. And I think that PuTTY also has a port for Linux. So I'm not sure what you're doing in the lab, but you can use something called PuTTY to connect a lab computer to a serial port. Now we're going to be connecting serial ports through USB as well. And so the USB has a driver in the Windows computer. And so if you look at the device management window, you can find what the driver is mapping the USB port to. So a lot of times it'll map, the driver will map to COM0 in Windows. And so then you point PuTTY to COM0, and then you set up PuTTY to receive a certain baud rate, and then you set up the PIC in your code to be the same baud rate. And then you turn power on the PIC and you hope everything's okay. And if it's not, then you close PuTTY, reopen it again, see if it works again. Then you uninstall the driver and reinstall it, see if it works again. So most of the time it works right off the bat, but with this kind of technology, there's always bus crashes and things that can go on. But so yeah, these are some common baud rates. The fastest one that I've seen, I think, is the 115,200, as in most newer computers. I should say most newer drivers. Okay, so RS-232 in the PIC has this block diagram. Basically, you write to the baud rate generator, and that sets everything up in the hardware. You have a UART receiver and a UART transmitter register, and those send and receive things on those pins. You can set up flow control for the request to send and clear to send pins. You have to set up those pins though, and I've just never used flow control for serial. I've never known anyone that used it. It's always, oh yeah, turn off flow control for that. So usually serial works just well enough that you don't have to do that. And when there's something going wrong, I don't feel like flow control would really help too much, but it's there, so it must be useful to somebody. There's something called IRDA here in the PIC. That's an infrared specification that uses RS-232, but it sends a clock. So it sends the PIC clock, and that's to make sure that things are synchronized a bit faster. So that will send it to an LED driver that drives an infrared LED. All right, so this is on the PIC side of things. So we talked about the mode register. There's a lot of bits in there. There's the top one, bit 15, is the UART enable. It enables the UART module. A lot of times when you're configuring things, you want to disable that right off the bat to make sure that the UART isn't reading the different status and different baud rate generator bits before it's ready to go. All this other stuff, FRZ, USIDL, we're not going to really use. One thing that we will use is the UART enable bits, they call it, which is kind of confusing. So they have one thing called UART enable bit, and another thing called UART enable bits. Those are bits 8 and 9, and what those do is they configure the different flow control modes. So for 00 is what we'll use. TX and RX pins are enabled and used. CTS, RTS are controlled by port latches, which basically just means you can use them if you want, but you have to do it in your code to configure them, which essentially means they're turned off, but they don't say that. So we're probably going to use 00 for bits 9 and 8. And then the other important bits are BRGH, which is the high baud rate select bit. It basically just changes the clock divide for the baud rate generator. When it's set to 1, then it's faster. What that actually means is it divides the instruction clock by less. Okay, so when it's set to 0, then it divides the instruction clock by 16 to put in the baud rate generator. When it's set to 1, it divides the instruction clock by 4. So it divides by less, which basically just means faster. So, parity and data selection bits. We're going to be using 8-bit data mostly. You can send 9 bits of data at a time, and I could see that being useful if you're sending and receiving signed numbers, basically, or if you just want to send more information, you have an extra bit. But we're just going to be sending bytes at a time. For characters, so how many bits are in an ASCII character for UTF-8? 8 bits. So if we're sending and receiving characters, we'll probably just use 8 bits. And that's what, when you type in a terminal server, you're typing ASCII characters. So you're typing bytes at a time. If you type an A, that's 8 bytes, or 8 bits. And so you can send and receive bytes at a time. You could also send and receive number data, and you could send chunks of number data bytes at a time. You can choose what you want that number data to represent, but it just has to be agreed upon on either side of it. Okay, so this is the mode register. Talked about that enough. Any questions about any of those bits in the mode register? There's something called a baud, which is an automatic baud rate generator, and that seems pretty useful. I'm not exactly sure what it does. I know we don't use it, but I might look into that some more. Okay, so the other thing we write is I think U1 sta means status. Yeah, U1 status and control register. So we've got transmit buffer full status bit, transmit enable bit, interrupt mode selection bits for receive and transmit. So the useful bits here are TX enable, I think, is the most useful, because that basically just enables the transmission part of the UART to send things. If you're doing interrupts, you can set the different modes for interrupt status. Okay, so for transmission, you can set it to 1-1, which is reserved. Well, I don't know what that means. It's reserved for something. I don't know what. You can set it to 1-0, which means an interrupt is generated when a character is transferred to the transmit shift register and the transmit buffer becomes empty. So that seems to make a lot of sense, because basically once the character is sent, then it sets the interrupt flag. So that means you're ready to put another character in the buffer. So that one seems to make the most sense. You can do 0-1, which is interrupt generated when the last transmission is over, last character shifted out of the transmit shift register, and the transmit operations are completed. So that seems to be similar, but I believe the transmit shift register can store 16 bits, so it could store 2 characters. So it could shift 2 bytes in succession. So if you wrote 2 bytes to the transmit shift register at once, this interrupt would shift one out, or the interrupt would get generated when you shift both out. And then 0-0 is interrupt generated when any character is transferred to the transmit shift register. This implies at least one location is empty in the transmit buffer. So the transmit buffer is what you write to. The transmit shift register is what shifts out the buffer one bit at a time. So it sends it out in the UARTs pin. So mode 0-0 is kind of like mode 1-0, but it's basically if you're using more than 1 byte in the buffer at once. So it'll just shift. It'll set the interrupt no matter what. Basically, it'll set the interrupt every time you send a byte out. So receive mode is similar. You have 1-1, that's the interrupt flag is set when the receive buffer is full. You got 1-0, interrupt flag bit is set when receive buffer is 3/4 full. That's 3 data characters. And 0x interrupt flag bit is set whenever a character is received. So to me, it kind of makes sense to set them both to 0, because then you're generating interrupts whenever you get a character, and it's potentially faster to set them up differently. But for simplicity, we'll just set them to 0, and then we'll send and receive characters one at a time. And what else do I want to say? Okay, so regardless of whether or not you want to use interrupts, the interrupt flags for these will be set. So it may not generate an interrupt, that is, it may not change your program counter if you don't have interrupts enabled, but it will still set the flag. So the interrupt flag for the UARTs, the interrupt flags are pretty useful when you're writing code. So you may, there's something called transmit buffer full status bit, which will be set to 1 when you write the transmit buffer. So that's when you send something in the transmit buffer. It doesn't necessarily mean that the transmit buffer has been shifted out, the TX pin. It just means in your code you wrote to it, and so that bit will be set when you write to it. The interrupt flag, on the other hand, will be set when you actually send the data. So the interrupt flag is more useful. So the interrupt flags are useful in general, whether or not you're using interrupts. They're kind of the thing that tells you whether or not the data has been sent or received. So the baud rates, in the manual they give you these equations for what do you write to the baud rate generator register to get the baud rate that you want. So one of the equations shows the actual baud rate that you get when you have a certain value. That value is going to be an integer. So when you write that integer to the BRG register, then you get that baud rate. And then it shows you the closest you can get with a specific baud rate. You round it to the nearest integer, and that'll show you the error. If you round to the low integer, then you'll always get a positive error. If you round to the high integer, then you'll get a negative error. So there's 2 different equations. One for BRGH bit equals 0, that's low speed mode. That's in the mode register. And the other one is high speed mode. And the difference is one divides the instruction clock by 16, the other divides it by 4. So if our instruction clock is 16 megahertz, or 16 million instructions per second, then the top one will divide it by 16, so we'll just get a factor of 1. The bottom one will divide it by 4, so we'll get a factor of 4. Okay, so here's, to me, the most important part. It doesn't really matter if you're in high speed or low speed mode. The max that you can do is 4 million baud. Let's see. Yeah, 4 million baud, I guess, in high speed mode. But the problem is you have to have a terminal that will receive that fast, and specifically a terminal that will receive that data rate. I'm sure some terminal programs you can just specify any integer or basically any floating point number for the baud rate. But for the most common baud, you have to get as close as possible. So to me, these baud rates, what I really want to look at is the error, so the percent error. So for 110 baud rate, there's 0 error, and for 250K baud rate, there's 0 error. So 250K seems like maybe a good baud rate, but the problem is I'm not sure if any any terminal servers implement 250K. If they did, that would be the ideal choice. So the other common baud rates are in here as well. 38.4, 115. So 115 is one to look at. So if we use BRGH equals 0, what's the error for 115? Yeah, negative 3% error. And if you look at the actual baud rate, we're off by 4K. So I'm going to guess that that may be allowable by most modern computers. But I'm going to guess that in that case, we're going to want to use BRGH equals 1. So what's the error with BRGH equals 1 at 115K? 0.62, so it's lower. So if you're trying to go as fast as possible for some reason, you want to set BRGH equals 1. But otherwise, I think you want to set BRGH 1 to be the lowest error. And it looks like in general BRGH 1 has lower error. I think in a lot of examples in the class we just set it to 0 because we're going to use 9600 and 0.16 is low enough error for our purposes. It looks like BRGH 1 has lower error in general. All right, that's what I've got for RS-232. The next half of the class I want to do an example, but I think we'll probably take a break first. Maybe come back at 9:10 or so.
I usually get there like about an hour early. So I'm just looking at the process. Yeah, just because I think it's simpler. Because the math is easier because you just divide the instruction frequency by 16, which in our case is 1.
him
Mhm.
the same email that we sent you for the link for the document. Try to,
Oh, really?
yeah.
Okay,
Shall I send you an email? Kind of.
that'd be great.
And then Monday works best for me.
That's fine.
And then I'll send you right after class.
Wait, this coming Monday is the 4th of July, right?
Usually Saturday, Tuesday, we have schedule. Let me email
Discussion,
you.
yeah.
Let me email you after discussion.
Mhm.
I think it's really far on my homework help. I got the business side and the marketing side. All four of mine. The other two are how to make. Oh, that's it. She also has to try and make good ideas with all these kind of scientific illustrations, but all these projects because I don't have files. Oh, right. Oh, they want to say what now?
All right, I guess let's get started again. So was anyone able to check out the video from lecture 6, I think? Anybody look at it?
Yes.
How was it?
It's what we taught, and it's not too clear.
Yeah, that's what I was afraid of. Is it helpful at all?
Yeah.
Okay.
But like when I ask a question.
Yeah, I gotcha. I'll have to think about what to do about that. I guess I could just repeat questions in general, but otherwise, for now, I think I'm just going to try to keep recording videos. I wasn't really prepared to record videos of the class, so I didn't really plan for it too much. But I might talk to IT and see if they have any solutions. And then last Monday, I had the same thing set up, but I never hit record, so there's no video for Monday. So for what it's worth, I think it's probably good for an audio record. To me, it didn't look like the video was very good, but it's something at least, hopefully. But I'm really hoping that I'll have a reading list up and enough practice problems that you'll have material to study and you won't have to look at the videos. Yeah. Yeah, the slides. Yep, I'll do that. And I think I might, I keep forgetting, but I might start just taking pictures of the board and then posting those after each lecture. Again, like I'm not really set up. I didn't really plan on doing this stuff, but I think it would be helpful. Yeah. I think that's what Kia did when he taught the course. He has this giant Word file that's his lecture notes, and it's kind of hard to decipher, but he just takes pictures of the board and sticks it in the file, and it's like getting close to a 100 megabyte file. But, I guess it's all there, so. What else? Yeah, I'm putting together a reading list that basically just has the relevant sections of the data sheet and other manuals for each lecture. So, yeah, so there's the data sheet, and then if you read the data sheet, it references other documents all the time. There's something called the Family Reference Manual, PIC24F Family Reference Manual, which is a series of like 20 PDFs for each chapter of the data sheet. I think the idea was to keep the data sheet short, but unfortunately they don't provide links to those other documents, so you just have to Google the name to try to find them. I'm going to try to put those all together in a folder in Moodle, so you won't have to do that, and then link them all up. And then there's the Programmer's Reference Manual, which is different from all those documents. The Programmer's Reference Manual kind of helps you write programs for the PIC. That's the name. But the Programmer's Reference Manual is the same for the PIC24F and the DS PIC30, as well as other PIC24s, PIC24E, PIC24K. So it's got all that stuff in the same thing. So it can be kind of confusing. That's a good question. I'm not sure off the top of my head. But they're basically just different performance versions of the PIC24 architecture. They might refer to different clock speeds. There's also something called the Microchip Wiki, which is microchip.wiki.com, I think. And that has lots of cool diagrams, and it's got links to everything on the left side. It's kind of like one of those web pages. So it's a lot faster than navigating through the datasheet PDF. I'll post a link to that on Moodle. It has a lot of good stuff for the PIC18 because it's a wiki and people know the PIC18 really well. For the PIC24, it has a lot of good stuff too, but it's a little frustrating in that it's missing, I think, the UART section, and it's missing some other stuff. So maybe I'll personally upload some stuff to that wiki for the class if I have time. Which I probably don't, but that's another resource. What else? I uploaded a practice midterm. Did anyone see that?
Yes.
Okay. I would like feedback on that. Maybe I'll put a feedback section on Moodle. But how do people think of the exam? Was it hard? Was it easy? Pretty good. Okay.
I'd say more on the hard end.
Okay. What did you think about writing assembly for that section?
That's why I said a little more on the hard end.
I think it was the solution was like 6 lines of assembly. But that's my solution, knowing that I had that in mind when I wrote the problem. So in an exam, it's kind of...
When I thought about it, I thought, hey, checking each individual one, I didn't think about going back to the...
Right, right.
So in my case, it would have taken a lot longer.
Yeah, maybe like 12 lines or something.
And so we have closer to 60.
Yeah, and I might let you write code on your computers too. Maybe I'll see what Kia did. The problem with I think for now, data sheet only on computers.
What about the programmers?
Yeah, data sheet, programmer's manual, that kind of stuff. That makes the most sense to me. And then the rest by hand, by paper or something like that. I think he let everyone write. I think he had a Word document that was the exam, and he let you write in the Word document. I'll figure out what I want to do. If it's going to be by paper, then it'll be shorter. So, and either way, I want you to know. I want you to just be able to do simple functions in the exam. It's an exam. It's like, I don't want you to feel like you have to solve these kind of hard problems under pressure. So it's more just like the basics. So yeah, I think there'll probably be like maybe 1 or 2 hard questions, and then 3 or 4 kind of single answer questions about various things in the pick. And I'll try to get another practice exam up, and maybe a 3rd one as well. And the real exam, may use problems from the practice exams, just directly. So they could be useful resources for people. I think it's going to be July 11th. Does anyone have problems with that?
Is that Monday or the Friday?
Monday. Yeah, it's on Moodle. So. Oh God. I will try to write it for a 1-hour exam. Okay, but you'll have the full 2 hours. I mean, discussion is Tuesday the 5th. I'm not sure. I guess I won't do lab that day. Do people want to do discussion next week? Would that be helpful for people?
I would like to have a day where we can go over the overview of the tests.
Okay, that will be the last discussion before the test, right?
Yes.
Should we make it like a code discussion review type thing since we all got computers? Okay. I'll do a code discussion. Yeah, so the exam is a week from Monday then, so it's coming up. Okay, so the exam, the hard questions will just be on writing C and assembly things. It's not going to be on the hard questions won't be on configuring UART stuff. It'll be more like reading and writing to data memory, moving things around. The sort of easy one-off questions, I might have 2 easy one-off questions about UART or interrupts, and I'll probably have 2 or 3 easy one-off questions about computer architecture. Okay, so just like how many bits, how many bytes, that type of thing. All right. What else? That's all I'll say about that unless there are questions. Okay. So for the last half of class, I wanted to talk about interrupts some more. And so there's a section of the PIC24F family manual on interrupts. And I basically wanted to talk about interrupt timing from the perspective of how long instructions take. So we talked about timing a lot early on, and our first lab was on timing. Our first 2 labs were on timing. How long do instructions take? And we measured it like with a stopwatch. So interrupts kind of, you might think that would screw up timing, and if you have a timing sensitive piece of code, it definitely will. So if you, we'll get into it. So if you're running your code, here's what interrupt timing looks like during a 1-cycle instruction. So it says here in the diagram, we have a peripheral interrupt event occurs at or before the midpoint of this cycle. So this is our code, our main code, and it's doing this instruction cycle. The midpoint means that so it's before we do the fetch step, or it's before we do the execution step. So we fetch this instruction. If it's before we've done the execution step, then we do the interrupt. So we've got the program counter +2 for the next instruction, and we save that in a temporary buffer. And it doesn't say where the temporary buffer is, but we assume that we save it somewhere. So when we come back from the interrupt, we'll know where to go. And then we go to the interrupt vector. So when the interrupt happens, it tells us which vector to go to. So we go to that vector, and we read out the address of the interrupt service routine. So the interrupt vector is a location in program memory, and it's just one program word long. And what that is the address of the interrupt service routine. So it goes to the vector, and then it goes to the interrupt service routine, which could be however many instructions long. So we fetch the vector, and it points us to go to the interrupt service routine, and that is the address of the function where we're actually doing all the interrupt stuff. Okay, and this shows when the interrupt flag occurs. So we've got the instruction before, we got the current instruction, save the program counter, go to the fetch vector, go to the interrupt service routine, and then we're starting to execute the things in the interrupt service routine. So we've got ISR, ISR +2, ISR +4. That's at the address in program memory 2000, which it could be anywhere. It's up to the compiler. Okay, so that's during a 1-cycle instruction. We got interrupted, and then we're going to the interrupt service routine. For 2-cycle instructions, it's pretty similar. We've got the program counter, the instruction PC for the first cycle, instruction PC for the second cycle. So it executes those 2 before we actually go to the interrupt. First cycle, 2 cycle. Okay,
So now we want to come back from the interrupt. What happens? So we've got the last instruction of the interrupt service routine got finished, and then we've got the retfee instruction, which is return from interrupt. It says pop low bits of 16 bits of PC to the RAM stack. So pop to me means you're returning it. So what I think this is actually doing is wherever we saved the program counter before, now we're putting it on the stack to get loaded into the interrupt service routine. Sorry, to get loaded into the program counter, and then we pop the high bits of the program counter. So the return from interrupt, basically wherever we saved the PC from before, we're pulling it back and then loading it up, and we do a no-op, and then we're ready to go back to where we were before, PC plus 2, PC plus 4, 6, whatever. So in principle, it's simple. When we do an interrupt, we just have to save the program counter to know where we need to go back to. But what about the other things that we might want to save that the interrupt service routine might ruin, like the working registers? See if that's in here. Okay, I believe it's in the programmer's model. Okay, here we go. Okay, so here in the programmer's model, it has a little section that's shaded. And it says below, these registers are bits shadowed for push and pop instructions. And so I believe what happens with the interrupt is these registers get saved in shadow registers. So when an interrupt happens, they can be used in the interrupt service routine, and then when you come back from it, they can be restored to where they were before. So they have extra registers associated with them so that they can be saved in the interrupt service routine. And it says that you can use a push S and pop S instruction to return those. Let's see if those are talked about here. Setup, control, register maps. Nope. Let's see. It's 0 to 3. Let's look at the programmer's manual. So let's do push S, push shadow registers. So the contents of the primary registers are copied into their respective shadow registers. This takes one cycle. So it takes one instruction cycle to save 4 registers. So if you want to save the 4 primary working registers, you can do this before an interrupt service routine, and it'll save all of them in one instruction cycle. But what happens if you don't know an interrupt service routine is coming, which you probably won't? What you can do is you can do this before, like the first line of your interrupt service routine. So let's see if the compiler actually does that. So here I've got, So here I've got the code that we looked at in the discussion section. It's got an interrupt service routine for receiving a character. Let's look at the disassembly for that. Okay, so this is the interrupt service routine. The first thing that we do is we move W0 onto the stack. And then we move W2 onto the stack. So here we're not actually using the push and pop shadow registers. In fact, the only thing that we're pushing and popping is something called PSV page, which is the location of something from program memory. I'm not exactly sure what. So let's look at the main function. So the main function, link 8, we're setting up a frame of 8. Then we're moving things to and from the frame pointer. Let's see where, okay, rcall getch. So we're moving some things from the frame pointer, so the compiler hasn't actually used push and pop instructions at all. I'm not sure why that is, other than there must be a compilation algorithm that doesn't need them, or maybe the compiler just only uses a limited instruction set for compiling things. But in the interrupt service routine, instead of using the shadow registers, they're using the stack to save W0 and W2 before the interrupt service routine. Then they're moving the frame pointer from before onto the stack with a link, and then all this other stuff, then unlink, and then we're popping, but instead of using the pop instruction, they are using W15 directly and the move instruction. Yep.
So, I'm guessing the push is equivalent to that move that D, whatever pushing it into it, makes sense.
Yeah.
Now, is it because it's that D that they did that D, or is that double?
Yeah, move.d
Move.d moves 2 words at the same time, so I'm not sure. It would push 2 word locations, so it would do 32 bits. So it could be that when you do move.d W15 minus W2, it does W2 and W3 at the same time, and then move.d W15 minus W15 W0, it does 0 and 1 at the same time because it's doing 32 bits. I'm not sure. I'd have to look at it.
So as you're pushing, you have to push W.
Yeah, you would do 4 things. Let's take a look at move.d. Yeah, so it moves WS to working directory and working directory +1. So it does exactly that. It does the 2 consecutive working directories. But the thing is, it takes 2 instruction cycles. So it's no faster than doing a pop. I don't know. I don't know why it does that. It is just 1 word of program memory, though, it says here. So with 1 word of program memory, you can do this. So it saves program memory. So I could see why the compiler would say, okay, we're going to do this. We're not going to do push and pop. I believe, however, there is a push.d. Let's take a look. Yeah, there's a double push. It takes 1 word and it does the same thing. Is it implemented for our? Yep, it's implemented for our thing too. I don't know. It does the same thing. I don't know why the compiler chose move instead of push and pop. Okay? Yeah, same thing. Then it does retfee, which is return from instruction, which returns the program counter from where it was before. Making sense? Clear as mud? Clear as mud. Okay. Should we do another stack example? Okay. Yeah. Okay. Okay, I'm gonna take pictures, right? Okay, so I think I'm gonna do this in assembly because that's an easier way of explaining the stack. So we've got func1, we've got main, and then we've got our call func1. In our main program, we're doing link 8. So we're setting up 8 spots in the frame, and then we're going to do move x 800 into the stack point. How should I do this? So I'm going to draw a bunch of stacks for each instruction. So this is x 800, and the stack pointer is pointing right here. The frame pointer, let's put at x 900 for the frame pointer. So the frame pointer is, let's see. Would you like me to write a bunch of stacks or a bunch of data memory locations, or can I write the same one and keep erasing it when things change? Yeah, I'll write the same one because that's kind of how it works in real life. Okay, so I've got data memory in here, and I've got let's put x 800 right here. We've got W15 pointing to it, and let's do the frame starting at x 900, and we've got W14 pointing to it. So let's do set up stack pointer, set up frame pointer. Okay. And we're gonna add, or we're gonna move. We're gonna do our call setup, which sets everything up that we want to. Then we're gonna move port B to W0. And then down here we're gonna our call setup, or our call, sorry, func1. And then we're gonna add W0 with W1 and put that in W0.
want to add the value on port B to something that we're getting back from function 1. Okay, so function 1 will return its value in W1. Okay, so move number 5 into, let's do this. Let's do our call square, and that will square the value in W1. Okay. And then return. Okay, so basically, long story short, we want to save W0. We want to return W1. Okay. And we better do an unlink. ULNK. Okay, so before we call function 1, what needs to happen? We want to save W0 on the stack. So we're going to do push W0. And after we call function 1, we want to return it. So we're going to do pop W0. Okay. So square square basically takes the value in W1 and squares it. So we're going to move W0 into W1 before we call square, and we're going to do link 2 up here. What do the link and unlink do in this code? They don't do anything because we haven't really used them. I could try to think of an example that would use link and unlink, but for now I'm just going to set up the frame pointer. Basically it's local variable space for each function that we're in. I know that's probably confusing, but just off the top of my head I can't think of a good example. Okay, so we're right here. We've got 8 spots for the frame pointer. So that's up to 0x9f for the frame pointer for the main code. So this is 8 spots for the. Actually, A, right? So it's up to this point. It's 8. Sorry. No, it's 6. It's 16. Sorry. It's 16 spots. So wouldn't it be 10 up to this point? Because it's 16 locations for 8 words to save. Or does this actually save just 8 bytes? Oh, damn it. I can't remember. So I'm pretty sure, if I remember correctly, it's words. If we're saving 8 locations, we want to.
4 words.
Well, we want to save 8 words. Yeah, so 16 bytes. Yeah, and I believe data memory is addressed
Yeah, link eight words, I believe. Does it link in words or bytes?
Word. No, bytes. It is a bytes. It's bytes. Enough size for 14 bytes. That should be 16.
Okay. So, yeah, it should be 16, or we could say we want to link 8 bytes. Is that okay? So, then this would be 0, 8. 8 bytes. Okay, sorry about that. Okay, so we just got to the frame pointer so far. I don't have enough time to finish this example. Can we do it next class?
Yes.
Okay. Great. Thanks. Then I'd like to maybe do an example next class too that uses an interrupt, and we can go through the same thing. I got more feedback forms if you